2, 1, welcome back. So derivatives of functions, now with a little bit of a sinusoidal twist. And we're going to be learning by examples. Now my assumption is that you are comfortable and familiar with the derivatives of sinusoidal functions, so just the basic ones, and now we want to be able to extrapolate it and start using product rules, quotient rules, and chain rules within derivatives that do have some sinusoidal twist into them. So my assumption is this, that you are kind of familiar. You know the derivative of sine is cos. You know the derivative of cos is negative sine, and so on. Now, some of these are sometimes hard to memorize, especially in the beginning, and don't feel bad. I actually forget them as well. The ones that I actually don't forget as quickly are typically these two. And once you know these two, you can pretty much derive all the other ones as well. Now, I'll put up a link up above there, and that is to the kind of derivation and showing you how the derivatives on the left that you see there, so derivative of sine, derivative of cos, derivative of tan comes about. And if you want to see the derivatives of cosecant, secant, and cotangent, I'll put up another link up above there so that you can refresh your mind on those. Now, once you have these, you can take on some pretty funky functions. And these functions, to be honest with you, they're not really realistic. I just kind of came up with them, but they do serve a nice purpose because of the fact that now we can apply, quotient rule, for example, in the first example, and also the chain rule applied in there as well. In the second one, we can apply the product rule, okay, or the quotient rule. You'll see that. And then the third one is, a combination of pretty much everything that we can come up with. Now, your teachers might come up with even harder functions, but I doubt it, because in the beginning, especially as you're just learning this, so in your first year calc, okay, and in particular maybe in high school, grade 12, so that introductory calc class, if you can take derivatives of these, okay, then you're pretty much good to go. Let's give these a try. So here's the first one. That is the first example that I want to be able to tackle. So I'm going to bring this down. It's a combination of numerous functions actually in here. So if you're looking at this and you want to take the derivative of here, we have quite a few things happening. So if you are looking at it, we have a quotient, right? So we have a numerator and a denominator. So we can use the quotient rule for this. So that's definitely one item that we're going to be able to use. And in that quotient rule, if you're taking the derivative of this entire thing, so with respect to x, so d with respect to dx of that entire item, this is what you would run into. So you can take the derivative first of your numerator, so that's what you see there up on top right there. And that derivative, well, the derivative of sine is nothing else but simply just cos, and it is cos, so you will have your argument, so 2x minus the pi still left in there. But you have to use now the chain rule to find out what the derivative of this is as well for the whole thing. So that is going to be just 2. So this is going to be multiplied by 2 because the derivative of 2x minus pi is just 2. And now you're going to be multiplying this by the actual, okay, square root of x. So that is the first part. So I'm going to be using the quotient rule there. And now this whole thing is going to be minus. Now, my sine of 2x minus pi is going to stay. And now you have to take the derivative of that square root of x. Well, the square root of x is not going to be fun. And please remember, so this is just x to the, really, 1/2. That's what we have there. So that's going to be 1/2. And then this is x. So I'll just keep it as it is. So this is going to be negative 1/2 over there. So that's that. That's what you are dealing with there. And then this entire thing is going to be all over my denominator. So this is going to be that. And this is supposed to be squared. And now if you square it, it's just going to turn out to be an x. And you can now manipulate this all that you want. So once you take the derivative, manipulating this entire thing to try to find out, massaging it, seeing if I can, work with something and it's going to give me something a little bit nicer. you can do that. But finding the derivative, this is it. Now the rest is just basically playing around with algebra and possibly some trig identities if you had to do it. But that's all that you would have. Now, within these particular questions, when you do have a little bit harder derivatives, please keep in mind that the derivative doesn't exist everywhere. And in fact, because our function, so you can see there that we do have a denominator, so clearly, we're not going to have a derivative existing at x is equal to 0. And also, the function is not defined at all for negative values of x because we have that square root. So the actual argument, that we have under the radical sign can't be negative. So this is really going to be just for x, which is greater than 0. That's what you would have in here. And that's exactly what you would find within the derivative as well. So just be aware of that, if you have to actually point out where this derivative exists. So clearly it will not exist within here for x is equal to 0. So it cannot be that. And it also cannot be, so within here, so it has to be greater than 0 as a whole, because we can't have negative values, because we're going to run into trouble over here, right? So that's going to be one of our troubles that we have over here. So that's another trouble that we're going to be running into. The sines and the cosines are fine. They're actually defined everywhere. We don't have them in the denominator, so there's no issues. But that's something that you have to keep in mind for yourself. So that is your first example. So it's just an application of a quotient rule and also a chain rule that you would have in there. So that's number one. Now the second example that we're going to run into, which is going to be this one. So let's take a look how we can work with this. So we have a 10, and then we have a secant. So again, we kind of have to remember these things, and don't be surprised, that you'll forget. So if I want to take the derivative, now it is with respect to theta, so I guess we're taking the derivative with respect to, d theta, so it's another way of writing this out. And you can do it in a couple of different ways. So yes, you can certainly do the product rule. So you would take the derivative of 10, multiplied by secant squared theta, plus, then the 10 theta would stay, and then you would take the derivative of secant squared theta. So we can certainly do that. And so within here, so kind of if I forget, so here's my 10, so it's just secant squared, and then the secant, I also have my actual derivative, which is secant x times 10x. So let's do that first. So I want to show you that we can certainly do that. This 4 I can just put right in front. And now, so 10 theta, so that's going to be, the derivative of that is just secant, squared theta. So that's what I have in there. So that's my derivative right there. So that's fine. And now this is going to be multiplied by secant squared theta. I'm just using the product rule. So we're going to have secant to the 4th. And now plus, now I have to keep, so I'm going to keep this. This is going to be 10 theta kept alone in here. And now I need to take, and maybe I'll change the color. So now I need to take the derivative of this. Well, that 2 is going to come up in the front. So this is going to be secant theta. And now I need to multiply this by whatever the derivative of secant theta is. But that's just, right here. So that's secant theta times 10x. So if I do that, so this is going to be secant theta times 10 theta. Now that becomes a little bit annoying and it becomes really long. So let me shift this back down over here, and I'll actually shrink it a bit just so that I can fit all of this in here. So this is going to be multiplied by now 2. Now notice the secant and secant. So this is secant squared theta, and then this is going to be my 10 theta. And surely enough, if I wanted to, I can combine all of this. So it's going to be 4 multiplied by secant to the 4th theta, that's this term, and then this one is going to be plus. Now you're going to have that 2 in front there, secant theta, so secant squared theta, and then the 10 and the 10, that is going to be now squared as well. And this is how you can take the derivative of that. And again, if you want to massage it in some particular way, you want to change the secant back in. So that would have been 1 over cos. If you wanted to, that's up to you, and then you can play around, but I think this is good enough. Now, you can also, if you forget, and this is what happens to me, and especially if it's on quizzes or tests or something like that, and then, I'm kind of nervous or I second guess myself, then I typically actually would change. So if I would have done this in a different way, I would have said, okay, well, I have 4. Now, 10, for some reason I can remember that 10 theta is sine theta over cos theta. And then secant squared, well, that is nothing else but 1 over cos squared theta. And this, right, is nothing else but 4. And then I have my sine theta all over, and this is going to be cos cubed theta. So if you're much more comfortable in taking derivatives of sines and coses, which typically most people are, they kind of remember sine is cos and cos is negative sine, then you can just use the quotient rule here and then get the actual answer, right? And then you can massage it back, once you take the derivative, and you can compare it to what we got over here, and it's going to be the same thing. So that's another kind of a hint for anybody who's taking derivatives and they do become kind of complicated. You start throwing around secants and tans and cotangents, okay, then don't stress out. You can always change them back to something that you're more familiar with if you remember kind of your sines and cosines, okay, and then the comparisons between them. All right, so the last example that we have, let me just scroll back up here. That's this one. This one looks like it's the most complicated one out of all of these. So I'm going to copy this. I'm going to bring this down within here. Paste it. Okay, so that would have been my third derivative, okay, that I would have. Now I have all kinds of stuff happening in this example. So I have, 1. Okay, this is like a product between these two right here. So we're going to have some kind of a product rule application. 1 is fine. So this one right here is not bad. That's just x squared minus 1. And then the other one is actually a sinusoidal, our little twist. But it does involve and also chain. We're going to have to use a chain rule because we have an argument of sine x squared. So let's give this a try. So like, how would we proceed? So first of all, we're going to take the derivative of this. Well, that derivative is beautiful. It's just 2x. That's going to get multiplied by, this is going to be cos sine x squared. So that is the first one. So by the product rule, plus. Now I'm going to have this x squared minus 1. And this is where the trick comes in. So once you do this, now I have to take the derivative of all of this junk right here. So what's the derivative of all of that? Okay, so I'll do it up there on top. The derivative of cos is negative sine. So negative sine of our argument. So notice I have a sine inside as well. That's sine x squared right there. And now I have to multiply this by the derivative of this, which is, so the derivative of sine is cos. So that's going to be cos of, and this is going to be x squared. And now again, another chain, so multiplied by 2x, which is from the x squared. So that's quite a lot. And now if I input all of this, right here, then I'm going to get my entire derivative. Now, that derivative is not going to look very pretty at all. So for example, what we'll have is, so this negative is going to change this. I'm going to just change this back to a negative sign right there. Maybe I'll use a different color. And now, if I'm trying to put this entire thing in here, it's going to be very hard for me to fit it. So that's going to be sine of, notice again, sine x squared times cos x squared times 2x. All right, so these are all multiplications within here. That's an ugly derivative that we have. Now, I didn't actually mention it for the second example, although we should talk about it. We also have to make sure that our derivative exists. right? In all, and where is it defined in case your teachers do ask you that. Now, within here, cosine sides are always good. We don't actually have any denominators, so that's fantastic. So we don't have to worry about any denominators at all. And within here, okay, even r, so notice we have a 2x in here. This is x squared minus 1. This is another 2x. So all of this is actually not bad. So we would have this, and it would exist for all x. So here, our derivative is actually defined on the entire real line. We don't have any restrictions in here. So that's pretty neat. Now, just for completeness, let's take this ugly thing, okay, and try to graph it on decimals. I'm going to just do one example in here just to show you, to see how it is. Hold on. Okay, so welcome back. So here it is. So it's pretty crazy in terms of a function. So here's the function. I'll make it a little bit bigger so that you can see it. Let me just move this out of the way. So, you know, as you can see the sinusoidal aspect coming up. It is dominated by 0, kind of by the x squared minus 1, which means if you think about x squared minus 1, it's nothing else but simply a quadratic, right? So it would be shifted by -1 down, and then it would just look like a parabola. But it's being multiplied by this cos sine x squared. So it looks pretty funky in here. Now it depends on how you stretch this out. So that's pretty neat. But in fact, it is defined everywhere. It just kind of starts to blow up on us, and it just keeps going higher and higher. Now, if you wanted to see what the derivative is, so the neat thing in decimals is, of course, you can just plot the derivative in this way. Let me get rid of this. And notice how crazy that derivative becomes. I'm going to try to see if I can span this out. All right. Okay, so I do have to kind of zoom in here. Okay, so that's what it is, and then it just starts taking off. Okay, and it gets higher and higher and higher. That actually is how the derivative looks like, but it is in fact defined everywhere. It's not a problem. I mean, it looks terrible, but it's not a problem at all. So that is the actual derivative. And again, when I am taking derivatives, I try not to simplify them. I know I did it for the second example, but overall I don't, because I'm more prone to making mistakes. And then I just typically just leave it, unless your teachers really want you, please simplify. We can certainly simplify this quite a bit, because I see we have a 2x, 2x, so we can factor that out. So that's fine. We have, what else? Is there anything else that we can factor possibly out? Okay, it doesn't really look like it. Okay, so this kind of is stuck. It is really an ugly function, but it is defined everywhere. So those are 3 neat examples, and I hope that if you watched this, you are capable of doing these examples on your own. I think the toughest part will be actually memorizing and doing enough examples so that you remember the derivatives of all your sinusoidal functions. And then applying the product rule, the chain rule, the quotient rules, those ones are not that bad. Sometimes you might forget, especially when it's chain rule. That has happened to me, that, I forget to still take the derivative of the argument within my function. All right, so thank you for watching. So this was a neat kind of learning by 3 examples, and if you can do these derivatives in your first year in terms of calc, then great. Okay, so huge thumbs up to you, and hopefully we'll see you in a future video. Welcome to 1mjourney.com. Bye everybody.